So far in the non-homogeneous differential equations we've looked at, the forcing function on the right-hand side has been either continuous or piecewise continuous. But there's another possibility leading to differential equations we can solve, and that's called an impulsive forcing function. So imagine that we have this non-homogeneous differential equation. And this forcing function on the right-hand side is an instantaneous force at time t equals a. So it's 0, 0, 0, 0. All of a sudden at time t equals a, it's a force, and then it goes back to being 0. So we're affecting the system only at that moment in time. So we're going to write this function. First of all, let's define delta of t, called the Dirac delta, to be a unit force at time t equals 0. So that means that delta of t minus a equals a unit force at time t equals a. So we can think of delta of t minus a as a function which is infinity at time a and 0 at all other times. And which satisfies the integral from negative infinity to infinity of delta t minus a equals 1. So we're supposed to be imagining a function which is always 0 except at a, and then it has an infinite value at time a, and then this dotted line above the open point on the x-axis is supposed to have area 1, because the integral of this function, well, it's 0, the function's 0 everywhere, and this one discontinuity is supposed to give us area 1 underneath an infinitely high dot, I guess. So this is not really a function. The infinite value is not allowed. But we're going to think of it as a function anyway. It helps to just imagine this picture and suspend disbelief temporarily and say that there's area 1 above this discontinuity. Now it's possible to show that for any continuous function g, the integral from negative infinity to infinity of g of t delta t minus a is equal to the integral from anywhere to the left of a to anywhere to the right of a. So let me write a minus epsilon 1 to a plus epsilon 2. So a little bit to the left of a to a little bit to the right of a, even a lot to the left of a to a lot to the right of a, as long as we're integrating over a. So any one of these integrals equals g of a. So that means that if we take the Laplace transform of delta t minus a as the integral from 0 to infinity of e to the negative st delta t minus a dt, and that gives us e to the minus sa. I'll write e to the minus as. So, sure, this is a weird function. Sure, it's not even really a function. It's sort of hard to picture. I mean, we have this picture, but we have to suspend disbelief when we think about this picture. Well, whatever's going on with it, it has an easy Laplace transform. And we can use it to solve differential equations. So, for example, let's solve the equation y double prime minus 3y prime plus 2y equals delta of t minus 1 with initial conditions y of 0 equals 1 and y prime of 0 equals 0. So, taking Laplace transform of both sides, we have y double prime is s squared capital Y minus s y of 0 minus y prime of 0 minus 3 y prime is s capital Y minus y of 0 plus 2y equals, now we have e to the negative t, negative 1t because it's t minus 1. Alright, so now we solve for capital Y, and we have capital Y times s squared minus 3s plus 2 minus sy of 0. Y of 0 is 1. So minus s minus y prime of 0, but that's 0, plus 3y of 0, so plus 3 equals e to the negative t. So that means y times s squared minus 3s plus 2 equals e to the negative t plus s minus 3, which means that y equals e to the negative t over s squared minus 3s plus 2 plus s minus 3 over s squared minus 3s plus 2. Now that polynomial in the denominator is s minus 2 times s minus 1. So writing the partial fractions should be pretty easy. So this is 1 e to the minus t times 1 over I'm sorry, this should be e to the minus s. I should have only s's in the equation now. So y equals e to the minus s over s minus 2, s minus 1, plus s minus 3 over s minus 2, s minus 1. And recall that 1 over s minus 2, s minus 1 is just 1 over s minus 2 minus 1 over s minus 1. So that's what's next to e to the s. And then s minus 3 over that, well, s minus 3 is really close to s minus 2. So instead of using partial fractions, I think I'm going to sort of fake it and write s minus 3 over s minus 2, s minus 1 equals s minus 2 minus 1 over s minus 2, s minus 1, which is s minus 2 over s minus 2, s minus 1, minus 1 over s minus 2, s minus 1. And the s minus 2's cancel here, so we have 1 over s minus 1. And then we know that this fraction is 1 over s minus 2 minus 1 over s minus 1. So that gives us 1 over s minus 1 plus 1 over s minus 1. So 2 over s minus 1 minus 1 over s minus 2. So y equals e to the minus s, 1 over s minus 1 minus 1, sorry, 1 over s minus 2 minus 1 over s minus 1 plus 2 over s minus 1 minus 1 over s minus 2. So that means that y, little y, is inverse Laplace transform of capital Y, which is inverse Laplace transform of e to the minus s, 1 over s minus 2 minus 1 over s minus 1. We can use the second shifting theorem to compute that. And then this is easy. So this is plus 2 e to the t minus e to the 2t. So we really just need to figure out what the inverse Laplace transform of this inside part is. Now by the second shifting theorem, the inverse Laplace transform of e to the minus s capital F of s equals u1 of t times f of t minus 1, where Laplace transform of f of t equals capital F of s. So f of s is this function function 1 over s minus 2 minus 1 over s minus 1 with no e's in it. So this is e to the 2t minus e to the t. So now we just need to multiply that by the step function u1 and then plug in t minus 1 wherever there's a t. So y equals u1 of t times e to the 2 t minus 1 minus e to the t minus 1 plus 2e to the t minus e to the 2t. So even though this differential equation had the Dirac delta in it, which is maybe the hardest function to visualize that we've worked with so far, solving the differential equation really isn't so hard. So these are not the hardest differential equations, even though they're based on maybe the hardest definition. The end.